Now we'll study about gas laws. Gas laws are basically laws established for a study and analysis of behavior of gases in different states. These laws we call gas laws. There are many laws which were established on the basis of several experiments. You can also write down behavior of gases in different states in various experiments. We'll discuss all these laws one by one. The very first is Boyle's law, which relates pressure and volume of a gas at a given temperature. You can simply state at constant temperature for a gas, its pressure is inversely proportional to its volume. Or we can write for constant temperature, the product of pressure and volume is a constant. We just substitute a proportionality constant and transform this expression into equality. It is PV is equals to constant. So we can state for two states of gas, we can use P1 V1 is equals to P2 V2 if temperature is constant. We just plot a graph between pressure and volume of a gas. Then from one initial state when pressure and volume are say P1 and V1, say gas is expanded, then it will always expand to another volume V2 where pressure is say P2 in a relation where P is inversely proportional to V, and the corresponding curve of P and V will be a rectangular hyperbola, which all of you know, that is for inverse proportionality relation, the curve is a rectangular hyperbola. Now in sequence, the second law is Charles and Gay-Lussac's law, and this law experimentally it was deduced in this law that for a gas at constant pressure, volume of gas is directly proportional to its absolute temperature, or we can also write V by T is a constant. And for two different states of a gas, we can state V1 by T1 is equals to V2 by T2. And if we plot a graph between volume and temperature for the gas, as V is proportional to T, the graph will be a straight line. Say gas pressure is constant. Say gas pressure is P1, which is kept constant. We can state in this equation at one point and at other point, say there are two states of a gas, X and Y, then volume and temperature ratio, say V1 T1 and V2 T2 are corresponding volume temperatures at state Y, then the ratio of volume and temperature remains constant. Say if we increase the pressure, we can state on increasing pressure, the straight line will change like this. In this situation, we can state if it is P2, which is also kept constant, then again volume temperature ratio remains constant, but the slope of this particular straight line at another pressure will decrease. Here we can state P2 is more than P1. This is quite important to understand why on increasing pressure the slope decreases, because we can state if we increase the pressure, the gas will get compressed for the same temperature, so the volume will be relatively lesser on the same value of pressure which was earlier, and it was less than the pressure which is present right now. So you just be careful about the situation what we have analyzed. Now based on Boyle's law and Charles Gay-Lussac's law, combining the two experiments, we can deduce another law which is ideal gas law, which is actually used for ideal gases for relating pressure, volume, temperature of a gas. But as we have studied in postulates of kinetic theory of gases that ideal gas law can be applied for real gases at all temperatures and pressure. So this law, as we have discussed earlier also, it is defined as PV is equals to nRT, where P is the pressure of gas, V is the volume, nR the number of moles, R is universal gas constant and T is temperature. You must be very careful while substituting these parameters about their units, like if P is taken in Pascal, volume is taken in meter cube, temperature which is the absolute temperature, it is taken in Kelvin, then the value of universal gas constant R we take as 8.314 joule per mole Kelvin. This is the value of R we use. If you change the units of pressure, volume, temperature, correspondingly the value of R also changes. But these are the standard international standard convention which we are going to use in SI units. And using this relation, we can also write the ratio of PV and the temperature is nR, which can be taken as a constant for a gas in a container. As we know, in case of a container, number of moles are constant, R is already a constant. So we can state pressure, volume and temperature are always constant as number of moles are constant for a gas which is contained in a container. And we can also relate for two different states of a gas. We can write P1 V1 by T1 is equals to P2 V2 by T2. Here we are not doing anything except the conservation of moles. Initial number of moles in a given state of gas are always equal to the number of moles in final state. We must write if no leakage takes place during change of a state. Because obviously when the gas state is changing and in between if some number of moles are leaked out, then the final value of this ratio will be certainly less than the initial value. You must be very careful for conservation of moles. You can use P1 V1 by T1 as P2 V2 by T2. If we use this ideal gas law, then we can also deduce a standard relationship at a standard temperature and pressure, which is generally considered as temperature to be 273 Kelvin and pressure is 1 atmospheric pressure, which is equals to 1.013 into 10 to the power 5 Pascal. At STP, if we find out the volume of 1 mole of a gas, then for N equals to 1 mole, you can easily calculate by using PV equals to nRT. The volume can be written as nRT by P. When you substitute, it will be 1 into 8.314 multiplied by 273 divided by 1.013 into 10 to the power 5. On calculating, obviously here the units of volume we are getting will be meter cube. This will be 2240 into 10 to the power minus 5 meter cube. And if we just rearrange the values, this will be 22.4 into 10 to the power minus 3 meter cube, which can be written as 22.4 liter. This is a very important and a standard result which you should keep in mind, that for 1 mole of any gas at a standard temperature and pressure, it occupies a volume of 22.4 liter. You can also write that always 1 mole of any gas at STP occupies a volume of 22.4 liter. This is a very useful relation which is going to be used in many various kind of concepts and numerical applications.